All right, time for another math problem using an 80s calculator. All right, so I did one of these before where I had this clock face, and the problem was figure out the distance between the tips of the minute and the hour hand at a certain time. Kind of similar starting point, and the question is if you have two objects that are starting from the same position in space and they're accelerating away from each other at certain angles, different acceleration rates, and they're accelerating for different amounts of time, and you want to say, you want to figure out how far apart are they after a certain amount of time. Okay, that's the question. So you can imagine like a spaceship, uh, I don't know, shooting off a rocket or something in one direction and it accelerates in the opposite direction or a different direction. How far apart are they after, let's say, 30 seconds or a minute or however long? That's the question. All right, so it's kind of a similar idea. Here's the math here, but let me start from the top. So here's the problem there. Here's the starting point, and you have two different angles, theta 1, theta 2, and the objects are going off in different directions, R1 and R2. The question is find how far apart are they, the distance of that vector. And again, it's vector math. Vector math is so useful for so many different things, and you can just see how it plays out. This is kind of how you start. R1 plus Rx, that vector gives you R2, so you can solve for Rx, which is this in the I direction and that in the J direction. Okay? And then if you want the length of it, it's just the square root of that squared plus that squared, I plus J. Okay? So you have distance of 2 and distance of 1, and then the angles going with it, and then the same for 2. But then where it gets, I have constant velocity, but forget about that. That's not interesting. This one's interesting where you have acceleration for specific times and rates. So the distance of these two legs is going to be a combination of the distance it traveled during the acceleration, which is 1/2 at squared. All right, so a1t a1 squared for the first one, plus the distance that it traveled for the remaining amount of time at a constant velocity where it arrived at that velocity after accelerating, because we're assuming they start from zero velocity. Okay, so it's the total t minus the time that it accelerated, which is the remaining time, times the constant velocity that it arrived at after accelerating, which would be a1 times ta1, okay? Same for d2, and then you plug it in to that formula. Yeah, that's pretty much it. Oh, and so the way I've written the program is, here's the storage registers. So in storage register 1 is theta 1, and then 2 is theta 2, 3 is the total time that you're questioning here. 4 is the 4 and 5 actually you can ignore because that's the case where there's a constant velocity, but we're going to ignore that. TA1 is in register 6, so that's the time that it accelerated the first object here, up here. Time of acceleration there. 7 is the time of acceleration for the second one. The acceleration rate for the first object is in 8, and then 9 is acceleration rate for the second object. And the program is there. Starts here, label 2 I'm calling it. You go down here and then over here, there, and then you finish up there. This is really very simple. It's just plugging in basically a program. It's not doing an iteration or anything, but you could change this around to iterate in different ways if you wanted to search for, tell me how long to wait so that they're 5 miles apart or something like that. Although you could solve for that right here pretty easily, but I don't know. Just thought it would be kind of fun along the lines of, the vector math, because that the problem about the clock face kind of brought. I was like, there's a different way to look at it. So I got it plugged in this one. So let's just do this example. All right. So I'm just going to plug in the storage registers real quick here. We got 30, store 1, 120, store 2, 30 seconds, and 3, that's the total time. 4 and 5 don't matter, but I'm going to put them in anyways. 10, store 4, 20, store 5, 5 seconds, store 6. That's the acceleration time of the first one. 10 seconds in number 7. 3 feet per second squared in number 8. 4 feet per second squared in number 9. Okay, and let's go sub 2. So let's see how far apart are they after 30 seconds. About 1,000 feet. All right, what if we stretch that and we wait 5 minutes, okay? So, wait, which one is it? Total time, 3. Okay, so in 3, all right, 5, so 300 seconds. I'm going to store that in number 3. Go sub, 2. After 5 minutes, let's see how far apart they are. $12,000 feet. 5,280 divide, about 2.4 miles apart. All right, well, there you go. Again, the math is smarter than the both of us, as my old high school math teacher used to say.